consequences of looking at different variables is biology?
Maybe we'll start.
Let's go.
Yeah. Okay. So start. It's a great pleasure to introduce David Nelson. He's a professor of most science departments at Harvard. Physics, applied physics, biology, biochemistry.
Biology.
And very well known for his work on various problems in statistical mechanics, all the way from low-dimensional superconductors to vortex physics, soft condensed matter, and more recently, tethered, it's not recently, it's quite a few years, tethered surfaces. So David came to Harvard in late 70s as a professor of physics after being a junior fellow at Harvard. For so many years, he won many, many awards. Maybe to allow him time to give the talk, let me just mention that he won the Oliver Buckley Prize in Condensed Matter Physics. That's the highest prize of the American Physical Society in Condensed Matter Physics in 2004. The John Bardeen Prize for research, theoretical research in superconductivity a year earlier. He was a MacArthur Fellow in the 80s, and most recently he was awarded the Bohr Institute Medal of Honor. He will talk today about polymers and feathered surfaces.
Thank you. So thank you all for coming. It's a pleasure to be back at Stanford. And I want to tell you a story today about a problem that has a rich history. And in a sense, it connects one-dimensional linear polymer chains. Here's a picture of a linear polymer chain, like polyethylene oxide or something, in a watery solvent. And as many of you probably know, it undergoes a random walk. And when you have a 2- or 3-dimensional random walk, there's a backbone of the polymer that meanders around. And if I have a local tangent vector here at position R1, and then some other tangent vector down here at position R2, as soon as you start thinking about random walks, it doesn't take long to convince yourself that the correlations between these tangent vectors, T of R1 dotted into T of R2, if we just do some kind of average, this kind of average is going to be falling off, and it typically falls off exponentially fast. So this thing goes like e to the minus how far apart these things are. In fact, you might want to just reparameterize it in terms of the arc length as you go along. So you go along a certain arc length. Here's another arc length at S1, S2. So you do this as a function of arc length. And this thing falls off like the difference between the two arc lengths, S1 minus S2, over some sort of persistence length. And this is nothing more than an embodiment of a famous theorem. It goes back to Landau in one-dimensional statistical mechanics that you can't have long-range order in some kind of one-dimensional system. And for a long time, it was thought that something similar must be happening. It goes under the name of the Merman-Wagner theorem, or the Hohenberg-Sidney-Coleman theorem in particle physics. It was thought that you had a similar kind of situation for a two-dimensional sheet. And of course, the famous two-dimensional sheet that many of you know about and may be working on is graphene. So if I have a sheet of graphene floating around, instead of the tangents, I could look at the normal vectors to this piece of paper. And then the same thermal fluctuations that would disorder a polymer might tend to produce an object like this, a crumpled object in 3 dimensions. And you would think that you couldn't have a broken symmetry in 2 dimensions as well as 1. At least that's what was widely thought at the time. And in fact, that's wrong for interesting reasons that I'll be talking about. And it's known that 3-dimensional sheet polymers, and graphene will be one of our examples here, have long-range order. There may be wrinkles due for various reasons. We'll talk about rippled surfaces, thermally excited surfaces. But if you look at an edge-on view, the thing is approximately flat. And the normals, there's long-range order in the normals, which you might have thought would be like Heisenberg spins, 3-component spins. There is long-range order in violation of some theoretical expectations. There's a broken continuous symmetry that violates various theorems for good reasons. It's not that the theorems are wrong. It's that when you have a shear modulus, as you'll see, new kinds of physics arises in these kind of rippled surfaces. And there's a nice, fairly recent review by Sinai and Bari about this seeming contradiction of a venerable theorem in statistical mechanics. So back in the ancient times being maybe the 1990s when people were interested in such things, this is actually even before the 80s, Russ Chianelli and others at Exxon Research would look at the so-called RAG phase of molybdenum disulfide. So now let's imagine we have covalent bonds. This sort of looks like a crumpled piece of paper. And at the time you could take pictures of it. It was probably atomically thin. People weren't measuring conductivity or band structure at the time, but such things existed. But then the field, as you maybe know, got a shot in the arm when graphene was discovered, I guess about, 25 years ago or so. And I got drawn back into this area due to some very beautiful experiments at Cornell University about 9 years ago from Paul McEwen's lab. And what Paul did, or Paul and his group did, was to take a thin ribbon, atomically thin ribbon of graphene, maybe 10 microns across. This is a magnetic pad, and it's going to be floating, it is floating around in a watery solvent, maybe with some surfactant added to keep it from sticking to itself. And then he could just watch this thing, and he could twist it using an ordinary refrigerator magnet. Okay, it's a tabletop kind of experiment. And if I can make this movie work in this context, we will hopefully see this thing twisting and turning. Now this is really an amazing material if you think about it. It's atomically thin. We've reached the Moore's law limit of thinness, at least in one of the 3 dimensions. And because it's 10 microns across, it has an aspect ratio of 30,000. So there aren't many materials around that have that kind of amazingly large aspect ratio. And I want to emphasize that you can take this graphene sheet and other kinds of sheets and make kind of a new class of somewhat mutilated metamaterials by laser cutting. And so here's another thing from this McEwen group. And hopefully, again, I can make this work. Yeah, that's a graphene spring. And you can see the dimensions of this thing. You can do 10,000 pulls on that and it won't break. It also, notice the strain on this thing. It's not just being strained by 1% or 2 or 3%, which is typical of many materials. Otherwise, they will break if you make larger strains. This strain is like 100%. And if you look carefully at what's going on in this graphene spring, it's all due to escape into the 3rd dimension. The springs are twisting and turning this atomically thin thing. And I'll talk about some very recent experiments by my collaborators in the groups of David Zapluski at Argonne and Daniel Lopez. And they've been actually making somewhat thicker objects. They're not atomically thin. They're 28 nanometers thick. And they have themselves lots of interesting cutting and interesting physical properties, which also lend themselves to large strain. And the needle is a little jerky. It doesn't actually do what the movie suggests. But you can see this thing is also escaping into 3 dimensions as you pull and relax back. And this is an amorphous sheet of aluminum oxide. And I'll tell you how they made it. They made it in a very clever way. I think it's clever, which will play a role in what I have to tell you about. I should also say that I welcome interruptions and interruptions and questions, not only from the distinguished professors. I know that Aaron Kapotulnik will need no encouragement to interrupt me, but graduate students and postdocs, please stop me. If there's something that's unclear, it's probably my fault, so just stop me and ask. And as you know, PowerPoint is a form of asymmetrical warfare. PowerPoint corrupts absolutely. So it's your job to slow me down. Any questions so far? Yes, please.
Did you say that looking at that movie, we can tell that it's moving in the third dimension?
Okay, well, you have to. It's a good point. If you blur your eyes, this thing up in the upper right. If you look at it, if you make a little paper model of it, notice it gets thinner as I pull. Okay, and if you look carefully. Maybe more careful, I had to blow up this movie. It's actually twisting and turning, and it's becoming fundamentally 3-dimensional. So you may have to take that on faith, but that seems to be what's going on in allowing these very large strains. Other questions? All right, so note the escape into the 3rd dimension. So with this motivation, I want to show you the outline of my talk. And what I'm going to try to convince you of, demonstrate here, if you like, is the death of Hooke's law. So Hooke's law is fundamental in physics. It's the law of a spring, of course. We just saw a graphene spring with holes in it. And you define elastic constants in such a way that they're independent of the sample dimensions. They are a material property. That's what we're typically taught. But I want to convince you that there are important circumstances where, in fact, the elastic constants themselves become scale dependent. And they depend on the system size in a very surprising way, and it's often a very strongly system size dependent effect. So I'll start by talking about the statistical mechanics of thin plates. The classical zero temperature theory goes back to 1904 and work by Foeppl-von Karman. This thin plate theory has in it a dimensionless number. This is the Young's modulus. This is the size of the sample squared. This is a bending energy, a bending so-called elastic constant. And this dimensionless thing tells you how nonlinear the problem is. When I crumpled this piece of paper, I think you won't be surprised to learn that's quite a nonlinear thing. The amount of the nonlinearity, the analog, if you like, of the fine structure constant, which would be an expansion parameter for quantum electrodynamics, is something called the Foeppl-von Karman number. It's a little bit like, how many of you know about Reynolds numbers and fluid mechanics? Do they still teach that at Stanford? Good. I'm glad to hear that. This is the analog of a Reynolds number for these thin sheets. And when it gets very large, it's a challenging problem, like figuring out this crumpled piece of paper and so forth. I'll then move on to talk about, there's a prediction here when you turn on thermal fluctuations of strongly scale-dependent elastic parameters. And then I want to talk about this new class of aluminum oxide rippled cantilevers that my experimental colleagues have been making by templating off, it turns out, off a silicon wafer. And you'll see where that comes in a minute. And so they're able to make these diving board-like protrusions. and sort of use a laser and excite them, calculate the characteristic vibrational frequency, and compare a very smooth, pristine diving board to one that has not thermal ripples, but frozen-in ripples that are constructed in a very straightforward and interesting way. So this is the control. This is what happens when ripples. We can see how they are different. And then finally, if there's time, I'll tell you about some interesting mutilations that trigger a novel kind of phase transition by looking at materials which sort of would naturally pucker or pop into the third dimension. This is a picture of one of these objects, and they're quite interesting, I think, because they can have a tunable coefficient of thermal expansion, which can either be positive or negative or zero, depending on how close you are to an Ising-like phase transition in these puckers. So that's where I'm headed. Any questions at this point? Okay, so here's a recapitulation of a 120-year-old theory due to Foeppl and von Karman, and it's really pretty simple. It basically, if you think of it in solid-state physics language, you have in-plane phonons, U1 and U2, of this thin sheet that can escape into the third dimension if it wants to. And then you have an out-of-plane phonon field F that goes normal to this reference plane. So there are three phonon fields. This is a flexural phonon. And then what you can ask in constructing a kind of solid-state physics type elasticity theory, you could ask, how do lengths change when I go from this reference sheet to this sort of warped object? So this was actually made with a 3D printer, but it's a kind of warped analog, and you could say, how do I describe, say, thermal fluctuations producing this warping? And you just look at the change in the length from this parameterization, and you discover that there's an energy that has two interesting parts. There's this nonlinear term that comes into a strain matrix. This symmetrized strain is what you typically learn about in textbooks. And that's certainly true in 3 dimensions or in a rigid material in 2 dimensions that's on a substrate or something. But in general, there's this extra term that couples the out-of-plane flexural phonons to the in-plane strain. And some of you, if you know for example, the London theory of superconductivity, or the Ginzburg-Landau theory of superconductivity, this looks like a vector potential. But it's a nonlinear thing that shifts the gradients of the phonons, and it comes in terms of this tensor, in terms of these two terms, mu and lambda are these elastic constants, which themselves go back to the 19th century. And then there's this other interesting term here, this bending energy that actually comes in as the Laplacian of F squared. So there's a very soft restoring force to these flexural phonons, somewhat stronger force due to this term here, which is the stretching energy, and it involves rotationally invariant contractions of this nonlinear 2x2 matrix. And so notice they talk to each other because the F appears inside the Uij.
How can I understand the meaning of F when my membrane is crumpled?
Good question. So in that case, what I would do, and I probably won't get to this, thank you for the question. What I would do is just look at the local normal. So I would do some kind of differential geometry treatment of this crumpled sheet, look at the local normal and take the F to be in that local direction. But we'll see that most of the things I'm going to be interested in today, things are flat. And so macroscopically flat, they might be wrinkled, but they're macroscopically flat like this thing and this object here. And so we have a well-defined normal, but in general there are ways of looking at this. And if you go to high enough temperatures, it's believed, although never demonstrated experimentally, that graphene will go through a crumpling transition where you would have to take into account the twisting and turning of the topology.
But F can also be multivalent then.
Well, if it's really crumpled and you insist on using this Mons representation, it will surely be multiple valued. But you can also look at an internal coordinate system. After all, this is a piece of graph paper. And if I just look at the blue lines on this graph paper, that's a coordinate system where everything is well defined. So it's a great question. I can elide over it for this talk, but in general, you would have to look at it, especially above the crumpling transition. Other questions? Okay, so let's ask ourselves what's going on here. The first thing we want to do is perhaps ask, with certain boundary conditions, what minimizes this strange nonlinear functional? How would I put on some boundary conditions and try to figure out what's going on? Here's Foeppl, here's von Karman. And what they did was they said, well, if you look at the nonlinear stress matrix, which is related to the nonlinear strain matrix in this way, at zero temperature, it satisfies this zero force balance condition everywhere. And so just like the no magnetic monopoles condition of electricity and magnetism, that means you can write this thing. Actually, in this case, it's an anti-symmetric, there's a summation convention, contraction over these two derivatives of an airy stress function. And so if you put that in, there's an airy stress function that describes the in-plane stresses. There's still this F field. And if you just do a little functional minimization over that nonlinear energy, you'll get these Foeppl-von Karman equations. They were discovered in 1904. Many of us think that Foeppl is kind of a doppelganger of Bert Helpert. It looks vaguely like him to me, my colleague. But take a look at these equations, right? They're nonlinear. And they involve chi and they involve F. The Young's modulus, that standard in-plane elastic parameter, comes in naturally, as does that bending rigidity, which controls the ability of these undulations to escape into the third dimension. And there's this nonlinear thing here, but there's also the Laplacian squared acting on chi with a source term over here in terms of F, which is nothing but the Gaussian curvature. So the Gaussian curvature of this elastically distorted membrane is acting like a source. It's kind of Laplacian squared version of electrostatics here. And then there's a bilinear term in chi and F that comes into play. And I'd like to pause and just remark on these amazing equations. They're actually written down in one of the volumes of Landau and Lifshitz's book on theoretical physics. But then they say they're impossible to solve, so we'll move on. They're actually a kind of simplified version of 2G general relativity, written down 10 years before general relativity. And they do involve extrinsic curvature, which wouldn't occur in general relativity. There are exact solutions available in only very special cases. Here is one of the few exact solutions. This is a 5-fold disinclination in a triangular lattice. It basically, when it gets big enough, looks like a cone. And this cone solution, you notice that at this point of 5-fold symmetry, which is a concentration of Gaussian curvature acting as a source on chi, produce these curved lattice lines, which are basically curved geodesics. So it's bending. These geodesics bend in the vicinity of this Gaussian curvature singularity. And I'll show you in the next slide. You can take these equations, rewrite them, rescaling them, and there's a single dimensionless parameter that controls how nonlinear they are. Much like the Reynolds number of fluid mechanics, which I'm pleased to see is still taught at Stanford. By the way, when I was told that at my alma mater, Cornell, somebody came up to Hans Bethe in the late 1930s and said, Professor Bethe, I'm ready for the call, but unfortunately I never learned fluid mechanics. And he said, don't worry, we're getting rid of it. And it wasn't that he didn't like fluid mechanics. He used it very much at Los Alamos to design the atomic bomb and stuff, but they needed room for quantum physics at that time. But anyway, it's still a very challenging, beautiful subject, very highly nonlinear. You can see that on this next slide here. I'm just repeating the Foeppl-von Karman equations. And the crucial thing about them is that this bending rigidity, which is typically rather small, for graphene, it turns out in some appropriate units, it's really, really tiny. It multiplies the highest derivative in the problem. And 1 over the Young's modulus. Young's modulus is typically gigantic for something like graphene. And its reciprocal multiplies the highest derivative in the problem. And if you just scale out the overall size and the Young's modulus and the bending rigidity in the appropriate way, what you get are these dimensionless Foeppl-von Karman equations. And here is this single dimensionless parameter, this combination, which is Young's modulus, system size squared divided by bending rigidity. And these are the equations that are quite nonlinear and quite challenging. So how big is this nonlinearity parameter? Well, if you take put in reasonable values for crumpled aluminum foil or this piece of paper that I was crumpling earlier, and this is the thickness H. This nu is a Young's modulus. It's a Poisson ratio. E3 is a three-dimensional Young's modulus. You put it in for a piece of paper. The Foeppl-von Karman number of a piece of paper, a humble piece of paper, is 40 million. And that's why figuring out the configurations of these crumpled things is a little hard, a bit of a challenging problem. And if you do it for graphene, if you put in the 0 temperature, our best values of the bending rigidity for graphene, which is I think about 1.2 electron volts, this Young's modulus here, take a 10 micron square of graphene, this Foeppl-von Karman number is 10 to the 12. So good luck doing perturbation theory in powers of 10 to the 12. Okay, so what do we do at finite temperatures? It's already hard at 0 temperature to solve these problems. Well, if you go back to that original model of stretching and bending energies, it's nonlinear to be sure, but the in-plane phonons only occur quadratically. And so what you can do is trace them out. And that produces this interesting massless field theory. So kappa is a bending rigidity, and here's a soft restoring force, Laplacian F squared. And now the Young's modulus comes out in front of this strange-looking transverse projection operator acting on the tilts. These are gradients of F, so you can think of them as little tilts of Heisenberg spins. And so what that does is produce an interesting interaction between these Heisenberg spins. If I have an undulation like that corresponding to a longitudinal phonon, there's a typical soft restoring force. But if you try to go this way, you have to tear the surface. And so the Young's modulus comes in, and that's ultimately what leads to some of the interesting science that I'll talk about. To see that there's interesting science, what we can do is just imagine we're not at 0 temperature, but close to 0 temperature, and assume that kBt over kappa is small, so bending rigidity is large compared to temperature. Just do perturbation theory. Here are some Feynman diagrams that come from expanding this chordic coupling, and you can get a renormalized bending rigidity, something Luca and Politi and I did quite a while ago. And if you look at it, there's a correction to the 0 temperature bending rigidity. It's proportional to temperature. That's good. And you can evaluate this integral if you want. And so it's proportional to temperature. It's actually inverse proportional to kappa. Kappa is typically pretty large compared to temperature in many actual systems. There's a 32 pi cubed. That's good for perturbation theory. But it gets multiplied by the Foeppl-von Karman number. So it gets multiplied for graphene by 10 to the 12. All right, good luck just doing straightforward perturbation theory. What you can do is to sum up the most diverging diagrams at every order in this perturbation theory. Here's the most diverging at second order, at third order, and so forth. If you sum that up, you get a self-consistent theory for an elastic, so-called elastic constant, this renormalized bending rigidity, would then appear on the right-hand side down here in the denominator. And if you just solve that self-consistent problem as a function of wave vector, so you look at the response to things as a function of wave vector, you'll find that the bending rigidity diverges. And it doesn't just diverge like some logarithm. In this two-dimensional problem, it's diverging like 1 over q. So there's a very strong dependence on, it turns out, on the size of the system, basically. And this is the essence of an elastic constant, which is not a constant. And when you have these problems with divergences, you can do self-consistent graphical summations. But a better way to do it, typically, is to use the renormalization group. And so there was a renormalization group done well before graphene was discovered, but eventually Ludisal and Radzychowski published a little manual on how to do these things, which became quite useful for graphene. So here's my energy with the stretching and bending terms, this nonlinear strain tensor. If I just do the partition function in a systematic way, as we were taught by Ken Wilson, once renormalization groups were imported into condensed matter physics from high energy physics, you discover running coupling constants. And they don't just run, they sprint. They are strongly scale dependent. And this is what I mean by kind of the death of Hooke's law for this class of materials that can fluctuate into the third dimension. The bending rigidity now depends on the scale. And there's a thermal length that tells you when that bending rigidity has to be looked at a little more carefully. There's an exponent eta, which is about 1, but details don't matter. But you can get a length scale, more importantly. It's kind of a Ginzburg criterion for this problem. You can ask when this correction is comparable to what it's correcting. And so that tells you there's a critical size embedded in this Foeppl-von Karman number, above which you better take the fact that Hooke's law has died seriously. And so if I go back here, you can see that this goes like L over this thermal length that you get by equating those terms. So here's the thermal length down here. What is this thermal length? Well, I'll tell you in a minute. I'll tell you now. For graphene, if you just put in graphene numbers, and I was unaware of this until Paul McEwen pointed it out, there's a bending rigidity which is fairly, this is room temperature that we're talking about here. There's a fairly soft bending rigidity, a very stiff Young's modulus. If you put this in, this number is about 3 angstroms. So if you have a piece of graphene that's bigger than 3 angstroms by 3 angstroms, you better pay attention to this. It has to be freestanding. It can't just be a stretched drumhead, which is interesting in its own right. And what's shown in these renormalization group is that these flow diagrams, this is Foeppl-von Karman fixed point is unstable. It's already challenging, but it's unstable to something else, which you can handle by various renormalization group tricks. And you find that the bending rigidity scales like the system size to the 0.82 power. This is the universal exponent, we believe. And then the Young's modulus actually softens. And you can sort of see that softening by just taking this wrinkled piece of paper. And it's got all the stored area in it because it's been fluctuating in the third dimension. So if I pull on it, it's actually very easy to pull, at least for a while, until it gets jerked taut. And so that's, in a sense, what's going on with this fancy calculation. And now the question is, what happens to one of these atomically thin objects like graphene? So here's a cartoon of a beautiful graphene cantilever experiment. The Cornell group uses these gold pads to sort of anchor things and manipulate what's going on. As I said already, for a 10 micron width diving board-like structure with these thermal fluctuations, the Foeppl-von Karman number is 10 to the 12. We've reached, as I said, the Moore's law limit of thinness. We haven't reduced the other dimensions yet, but it's extremely thin. Aspect ratio of 30,000. And if you put in these numbers, as I said, the thermal length is 2 or 3 angstroms. Now, what about experiments? Well, there's this classic cantilever experiment inspired by Galileo. So this is one of Galileo's treatises on 2 new sciences, and one of them I think was mechanics. And here's his version of the cantilever experiment. But of course, here at Stanford and many other places, we like to work on smaller objects than this macroscopic thing. And so what they did was to look at the deflection, and also they turned the ribbon on its side and looked at the fluctuations in a perpendicular direction. Either way, you get a measure of this bending rigidity. You get a measure of this thing for different lengths. They always had the same width. And when you track these different spring constants for this vertical displacement, they in fact all fall on a nice line that goes like 1 over L cubed. That's expected. But the amplitude is about 4,000 times bigger than you would have expected at 0 temperature. So in fact, there's a huge amplification. This is what's expected as a function of the width of this ribbon. This is the scale-dependent elastic constant. But unfortunately, they never varied the width. They just measured it for a particular 10-micron width and said, whoa, that's big. And it's consistent with this theory that I've been telling you about. But I want to show you now a very recent experiment where my collaborators have ingeniously developed, I think ingenious, it wasn't my idea, but they thought of making their own kind of warped or rippled surfaces. So this is an example of such a rippled surface made with a 3D printer. I'll start passing this around. How did they make this surface? Well, I thought it was pretty clever. They basically take one of these silicon wafers. Okay, this is a major part of modern technology. You can buy this it's a single crystal of silicon. You can buy it for $20. And people typically use the polished side of this thing it's been polished exquisitely, uniformly with all the lattice planes lined up. But there's a rippled backside that never gets used. And so what they did was to take this as a template, the silicon thing, and grow aluminum oxide on both the front side and the back side. And it's not quite the same problem because there's quenched randomness in the ripples in the plastic thing that I was passing around. I hope to get that back at the end. There's quenched randomness, but the quenched randomness has this interesting power law form that's somewhat reminiscent because this exponent is very close to 4. It's just a measured rippling of the backside. The front side it has some roughness, but it's down by 3 orders of magnitude. The polished mirror-like side is very smooth. So that's going to be a control. And what these guys were able to do, using that silicon wafer, and Aaron said the $20 is too much. Now it's probably a huge markup. So this is the front side that everybody uses to make devices. They made a little aluminum oxide diving board from the top side. On the back side that most people don't use, they made one of these rippled things, a rippled analog with the same dimensions. And then they could vary systematically the length and the width, and to see really what's happening with these elastic constants. Are they scale dependent? There's an analogous theory for this quenched problem that you can look at. And so here's some of their results. These green things are the dimensions of the diving board. You can do it as a function of the length of the diving board, and then the expectation is because the width is always constant, that's what controls this anomalous elasticity. The elastic constant doesn't matter. The blue is the control. That's from the smooth side. The other side is from this other data. This red data is from the rough side. And now you can see that if you just do the standard textbook measurement of a renormalized bending rigidity, renormalized by these ripples, it's scale dependent. The wider it gets, the stronger it gets. And and it can also vary, have square driving boards. You can vary the thickness. And there's a theory that is a simple generalization of what I showed you already from the renormalization group of these quenched random ripples. And not only is there a scale-dependent elastic constant, there are sample-to-sample fluctuations. This is not a self-averaging system by a long shot. And if you want to get a sense of why this quenched stuff might lead to very large renormalization of the bending rigidity, I invite you to take a piece of paper, look at this pathetic piece of paper. It cannot hold up its own weight. Okay? But it's the same piece of paper that was now crumpled. And if we think of these, this crumpled thing, it's very strong. It has no problem holding itself up. And we have a theory of how the strength of this grows with size. And so that's why we need to revisit Hooke's law. We already knew that metallic films in 2 dimensions had a scale dependence, but typically that's logarithmic. This is a much stronger effect. It's basically approximately linear in the size. Yes, please.
So maybe this system not so much, but like in the graphene.
Yep.
You know, when you cut these boundaries,
Yep.
it's kind of an experimental question. Mechanically, is it kind of nothing interesting, or are there situations where it looks like there's a kind of a line energy that is substantially different?
Well, okay, that's an interesting question. I don't think they looked carefully into that. I suspect that the graphene cantilevers in the McEwen group had grain boundaries, for example, and so if you cut certain angles with respect to the grain boundaries, there could be an interesting, perhaps weak dependence on that angle. As far as they can tell, they do it many, many times, and there's not a qualitative difference when they cut. But that's certainly something to think about. What's going on at the edge? Could it get frayed? And of course, they sort of did it with a vengeance when they made this graphene spring with lots of holes and then very fascinating elastic properties. Other questions? Okay, so they compare, just a summary, compare the smooth versus the warped membranes, and you get this linear dependence, and we get very large sample-to-sample fluctuations, which are predicted to grow linearly with distance as well. At least we have an example where, because of the out-of-plane flexural phonons, you better take Hooke's law, this venerable Hooke's law from 300 years ago, with a fairly large grain of salt. Okay, another interesting thing. I'm going to go back to the thermal problem. We know a lot more about the thermal problem. And I want to now try to convince you that there's another interesting thing, which is, or another interesting material property, which is fairly rare. It has a negative coefficient of thermal expansion. And for those of you who knows about polymers, maybe you're not surprised. So here's a wrinkled blue sheet on top of a white 8.5 by 11 sheet of the same dimensions. Its projected area is smaller. And now let's imagine we do a little more sophisticated calculation. We can put a tension on the edges. We can look at the out-of-plane flexural phonons. This is like a phonon propagator. This exponent that controls the renormalized bending rigidity comes in. The important part of this fancy formula, which is just a formula for the shrinkage in the area, is this black term here. So you don't have to pay attention to this other stuff. This is nonlinear, interesting nonlinear powers of the stress come in here. This is not, like 3. This power is some fractional thing that depends on this exponent eta. In any event, if you take away the external stress and just look at the shrinkage due to thermal fluctuations, we can calculate that fairly accurately in terms of, this is like a 1 over a lattice constant. Here's the thermal length. And then what comes out in front is a negative number. So what that's basically saying is that as I change temperature, the thing shrinks. It's shrinking for entropic reasons. This is the prediction for the coefficient of thermal expansion. This is what you find in the textbook. But this is a 2-dimensional system that can fluctuate into 3 dimensions, so it's somewhat unusual. But even a solid-state physics system like graphene with covalent bonds is going to shrink, just as this little cartoon up here suggests. And so with no adjustable parameters, basically, we can look at the area as a function of temperature. And this is a computer simulation by Paul Hanakata, a test of this formula. And it's basically, it's in silico, not an actual experiment, but it's bang on. And so the thing shrinks. Now, maybe you don't want it to shrink. Maybe you have a cantilever application in mind. Maybe you want it to be very stiff, so you put in these undulations so that it stiffens up, much like this wrinkled piece of paper. But you don't want to have its dimensions change. You want to have it be reasonably insensitive to changes in temperature. There's a trick. And the trick involves looking at atomically thin, what we call atomically thin metamaterials. And there are people here who know how to make such things. We were inspired a little bit by lead sulfide, but more so by tin oxide, which in principle you could make a monolayer of. And then people maybe made a few layers, maybe not monolayers. And this is an alternation of tin and oxygen. And because they have a different size, you might imagine that under some circumstances, the bigger of the two atoms will escape into the third dimension. So let's imagine a some sort of square array of tin oxide. This is a little model that involves springs in 3 dimensions with preferred bond length here. These are the normals. These ends are the normals to neighboring triangular plaquettes in this little arrangement here. And we're going to model a big atom by just taking its bonds to be, say, 2% longer or 5% longer than the background matrix in which it's embedded. And if I just have one large, say, tin atom embedded in a lattice of oxygen or vice versa, we can look and see what happens. And it turns out, for this problem, there's a local Foeppl-von Karman number, which is the extra area associated with the large atom times the Young's modulus divided by the bending rigidity. And as you vary the length of these bonds, that's sort of the control parameter that varies this area, what you can do is actually see, for an isolated object, a buckling transition. As I crank up that Foeppl-von Karman number, this atom tries to escape into the third dimension. Now, what happens when I have a whole array of them, when I have a checkerboard array of these things? It turns out that most simple models of how these dimples interact with each other, actually, here's a child's toy. I won't bother to pass it around, but here are these little puckers, right? This one goes up, this one goes down. I could make an antiferromagnetic arrangement of these puckers. And the puckers, neighboring puckers, talk to each other. They talk to each other through the nonlinear Foeppl-von Karman elasticity. And if you look at that, as Abby Plummer did for her thesis, you'll find that there's an antiferromagnetic interaction between neighboring puckers. You could also imagine not lengthening the bonds. You could shorten the bonds. And if you shorten the bonds, and this is actually done in a triangular lattice, you get this kind of hyperbolic singularity. You can have a regular lattice of those guys, of shorter bonds, embedded in a background of larger bonds. Well, you don't have to worry about this at Stanford, but when I was an undergraduate at Cornell, we often saw tacoed bicycle wheels in the winter. And I don't know what the actual cause is, but you might imagine that the spokes have a differential thermal contraction during a cold Ithaca winter compared to what's going on out here. You could get this hyperbolic thing. And we've found lattices of hyperbolic stuff as well as these puckers. So now the question is, suppose I heat it up. What's going to happen? I go to very high temperatures, the thing will crumple, and in fact, if you look carefully, at a computer, a fairly sophisticated computer calculation, this is 120 by 120 lattice of puckers. This is the staggered magnetization. What we've made is a mechanical analog of an Ising antiferromagnet. And so as we heat this thing up, something's going on, and there actually is good evidence for a phase transition that's happening over here. If I have it, yeah, this might work. Let's see. Yeah, there's a bunch of puckers. They're all talking to each other. They're desperately trying at low temperatures to be antiferromagnetic, but as you heat it up, then entropy wants to have the usual Ising model disorder. These are not barcodes. These are Ising spins in our mechanical analog of a metamagnet. There seems to be an antiferromagnetic phase transition riding on top of the background of these fluxural phonons. So one question is, does this change the Ising phase transition that Onsager found for a rigid, incompressible Ising model? And we think it probably does. So here in this staggered magnetization is where we think the TC is. There's a specific heat-like singularity there. And here's our little mechanical Ising antiferromagnet. And now you can redo the area as a function of temperature. And it's not monotonic. When these puckers are disordering, the system stops thermally shrinking, but it expands. Why does it expand? Why does the area go up and then down again? Eventually it goes down. Well, one analogy I like is packing bowling pins. So if you're packing bowling pins in a box, you want them to be antiferromagnetic because they fill up the space very nicely. And if I randomize the orientation of these pins, the volume in this case would swell. And so near this Ising phase transition, in fact, the area relative to some reference area at 0 temperature goes down, thermally shrinking, then has the phase transition. It goes up, and it goes down again. And so you can tune, by going close to this phase transition, the coefficient of thermal expansion, which is just the slope, to be 0. And here are the two contributions that in a simple kind of renormalization group enhanced Landau theory that we find. And here is the actual coefficient of thermal expansion, the derivative of these curves, is a little bit noisy, but you can see it goes through 0. So you can actually, there are other materials you can do this, like water above the freezing point. You can get the coefficient of thermal expansion to vanish. Here we can also get it to vanish. Okay, so let me finish up by just summarizing our conclusion for this mechanical analog of an Ising antiferromagnet riding on a background of phonons. This is the susceptibility, the response function for the staggered antiferromagnetic order. It seems to diverge in a way that varies in a sensible, understandable fashion with the size. This is the specific heat. Okay, so, and then we can look at these exponents. And so here's our susceptibility. There's a standard finite size scaling tricks for getting these Ising exponents out. And we're pretty sure that, in fact, this system is in a different universality class. In fact, if you look at the specific heat over nu, it's a small value, but it's 4 standard deviations away from 0. So it's that, and Onsager found 0. So we think it's a different universality class. The renormalization group calculations which tend to support this conclusion. And how many of you have taken a course on the Haslam renormalization group? Anybody know about recursion relations? Okay. Well, for those of you that are interested, I've used it a number of times. Here are 2 sources of a perspective on the renormalization group, which is actually, it's at the 50th anniversary of when this technique migrated into condensed matter physics, thanks to Ken Wilson and Michael Fisher picking up on ideas of Leo Kadanoff. And here's a nice book, I like it anyway, that is sort of memories of him and how this science sort of changed the way we think about condensed matter physics. It's a way of doing kind of hydrodynamic coarse graining in a systematic way, reminiscent of the thinking that produced the Navier-Stokes equations, but now much more generally applicable. And in a shameless effort of self-promotion, another source is this book, which is coming out in, we hope, in early 2025 by Grace Zhang and myself on applications of the renormalization group to condensed matter physics. This is a quantum critical point. This is migrating flock of birds, active matter. This is, of course, graphene. And with that, I will stop and thank you for your attention.
This may reflect my misunderstanding, but let me, if I understood most of the discussion, it was a continuum descriptor.
Correct?
And if you think about the lattice examples, are there scales and issues qualitatively that come up due to non-locality as I get to this discretized scale?
Okay, so indeed it's a kind of long wavelength acoustic phonon like description of what's going on. Except for this Ising model, because here the puckers are occurring in alternating fashion on the scale of the lattice constant in our model of tin oxide. So we can put in that kind of stuff. A lot of times we're doing something which is sort of analogous to the Debye theory of the specific heat, where we'd say, well, they're phonons, and we sort of know roughly how they behave. They bend over near the zone boundary and all that. That can easily be put in here, and we had to do it for this antiferromagnet. So I think that's under control. David.
So what if, just to be perverse, you didn't want wrinkles?
Okay.
So I have two questions. One, do you have some ideas for how to try to either prevent a membrane from wrinkling or to remove wrinkles? And the other, specifically, if you put a membrane on a thicker, very smooth surface that it has a high adhesion energy.
Yeah.
Say for a nitride.
Okay. Yeah. Good. Okay. So there are two aspects of your question. One is if you put on a substrate, then these flexural phonons acquire a mass because they want to be at a certain distance from the height. So if you linearize about that, they'll just be an F squared term, and all this fancy stuff about Laplacian of F squared with the bending rigidity is going to be higher order, less important. So for the things I'm talking about, they have to be freestanding, like the cantilevers, the diving boards, and so forth. If I want to get rid of this, I need to pump up that thermal length scale that I talked about that turns out to be 2 to 3 angstroms for freestanding graphene. For a general material, it depends very strongly on the bending rigidity. And the bigger the bending rigidity, the bigger that length is. And the bending rigidity goes like the cube of the thickness. And so I would just make thicker objects. And so, there's a trade-off depending on what you want. My colleagues at Argonne and Penn State imagined that, okay, they get a 25-fold enhancement by putting in their ripples, by templating aluminum oxide off the rough side of one of these silicon wafers, and they imagined cutting it and tailoring it down and sculpting out a material that has an intermediate bending rigidity. And so, it depends on what the application is. If you want to have something that's going to be a sensor that has a certain resonant frequency, you want to be able to tune that. Maybe this is too big, then you cut it a little bit and get somewhere in between the 25-fold enhancement and the bare bending rigidity that you might have gotten or expected from density functional theory and so forth. Okay, there's a question there, and then in the back. Yes, please.
So 2 questions about this silicon thing that you passed around. So
Yeah.
the backside of it, the one that's ripple.
Right.
You said that the height of that one has correlations that go like HQ, H minus Q, like 1 over Q to the 4.
Approximately.
Where does that come from?
We don't know. I've asked these people, like, you know, how do you get this, you know, what is the source of this parallel? Well, there's something in the manufacturing process. It's self-similar. It seems to be a fractal. Oftentimes when you have cleavages or manufacturing things, for some reason you do get fractal stuff. When you polish, you also get 1 over Q to the 4, but it's down by, the amplitude is down by 3 orders of magnitude. So the short answer is we don't know, but conveniently for us, 1 over Q to the 4 is just what you would expect, first approximation, from thermal fluctuations and bending rigidity. Now the temperature, the equivalent temperature, the effective temperature associated with something like this, you know, turns out to be 100,000 degrees. It's just frozen, and so it's not true thermal thing. But it's a great question, and the short answer is we don't know precisely, but it's been measured very carefully. And both sides have it, but one side is 3 orders of magnitude bigger if you don't polish. All right, there's a question in the back, yeah.
Are there any materials in which your puckers would sit on a triangular lattice instead of on a
Definitely.
lattice?
Definitely. We scrupulously avoided triangular lattices because, as you probably are alluding to, a triangular lattice is frustrated so that if I have 3 points of a triangle here and I have a pucker that's up here, and then antiferromagnetically it wants to be down here, over here it has no idea what to do. So it's frustrated. And so you can guess, based on work on frustrated, simple Ising antiferromagnets, what might happen. You often get rows of up puckers next to down puckers. You get ripples in a particular direction. So that would be my guess, my best guess for what would happen at low temperatures there.
Related question, is it possible to have a local defect that gives you a ferromagnetic interaction, or the interactions of the
There are some regions, rare regions in phase space where we get a ferromagnetic interaction. And there I haven't looked carefully, but if they're all on the same side, you could imagine that would produce some macroscopic Gaussian curvature, and the thing would curve around to form a sphere. And so it's quite interesting, but we stayed away from it.
No more questions? Yeah, yeah.
This observation of the breakdown of self-averaging I thought was quite interesting. Is there sort of an intuitive reason why that?
Well, so the experimental evidence is very compelling. They make 30 of these things, and they plot, you know, they line up all 30 of them, and then they plot the bending rigidity. It's always, you know, large, of what are 25 times bigger than a polished, beautiful, flat thing. But they're scattered, and then you make them bigger, and they scatter more, and they scatter more. So I guess I would say, you know, when the fluctuations in the height that you get from that 1 over q squared is comparable to the thickness, that's when the self-averaging breaks down. And again, you know,
Logarithm number?
sorry?
That's the logarithm of?
It's a quenched random average where you have an average over the disorder, and probably can be related to the derivative of the logarithm of the partition function in the usual way. Yeah, so that's what the calculation was done. It's summing a bunch of Feynman diagrams, and it's predicted that the variance, the standard deviation, I should say, also grows linearly. So the bending rigidity is growing linearly, and the standard deviation is growing linearly. And I might even have evidence for that if I back up enough here. Let's take a quick look. So go back. And I go back before I did this kind of stuff, and even further back. And here, the strong scale-dependent sample-to-sample fluctuations. So this is the standard deviation of the bending rigidity from its background value, 25 times larger, and grows linearly with system size. So self-averaging, death of self-averaging, as well as death of Hooke's law. Too bad, but it's worth knowing about if you're trying to make a device. Yes?
Sorry, so I think I didn't quite follow the crumple sheet part.
Okay.
So how does the crumple sheet sustain itself? Is it locally plastically deformed?
Oh, okay. So the crumpling transition, much as I would wish otherwise, has never been observed in graphene. If you take a simple back-of-the-envelope calculation and say, when is the entropy of the fluctuations of the normals in this flat phase going to be enough to produce that? The answer is about 20,000 degrees Kelvin. And so that's very hard to obtain in a lab, even at Stanford. And so if you got up to 20,000 degrees Kelvin, you'd be breaking the covalent bonds. You could still try to get it by cutting out a regular lattice of perforations. And if you remove about 80% of this, my colleague Mark Bowick and David Yalanis have studied this. If you just put a regular lattice of holes in this thing, it will no longer crumple at 20,000 degrees Kelvin, it will crumple at 1,500 degrees Kelvin, which might be more accessible in the lab. And then, boy, if you could crumple graphene, you'd have a baby version of general relativity with Dirac cones for the electrons. So it's quantum mechanics, fluctuating geometry. Doesn't get any better than that. So here at Stanford, I have hope that somebody will actually make this thing crumple, and we can start asking interesting questions about crumpled sheets. Put a lead on this end, lead on that end. What are those electrons doing near the Dirac cones? Well, it's some kind of quantum mechanical thing coupled with geometry. That's a cool, and you do it on a tabletop, right?
So I think that after the funeral of Hooke's law, which is just after the talk, we will all go to the lab to crumple.
Right. Good.
Thank you, David.
You're welcome. I want to say hi to Bob. Nice to see you again, my friend.
I'm so sorry, but I had a class that
No worries.
way over.
No worries, no worries. Nice to see you.
Superb showmanship.
Well, I can't match you, Bob.
Well, maybe not, but remember, I was a student.